Hello there, and welcome to the Slumbering Archive. I'm so glad you found your way here tonight. If you've had a long day, if you're ready to let your mind wander somewhere peaceful, somewhere vast and quiet, then you're in exactly the right place. Tonight, we're going on a gentle journey through our solar system, through the silent order of our cosmic home. You've got nothing to do but rest, nothing to memorize, nothing to accomplish. Just let these facts about our celestial neighborhood wash over you like a calm tide. We'll explore 100 quiet truths about the planets, the moons, the spaces between. Some will surprise you, others will simply settle into your thoughts like dust on ancient stone. There's no rush here. No urgency, just the slow revelation of how our corner of the universe arranges itself piece by patient piece. So find your comfortable position, let your shoulders drop, and let's begin this exploration together at the pace of starlight crossing the dark. If these explorations help you unwind, if they give your mind a place to rest at the end of the day, consider subscribing to the Slumbering Archive. It helps others find their way here too, to this quiet corner where science meets sleep. I'm curious, where are you listening from tonight? Perhaps you're watching the same stars I am, just from a different angle on our spinning world. Now let's turn our attention outward to the system that holds us. Our solar system is approximately 4.6 billion years old. Think about that number for a moment. 4,600 million years. It formed from a massive cloud of gas and dust, what astronomers call a molecular cloud. This cloud was drifting through space, minding its own business when something disturbed it. Perhaps a nearby star exploded in a supernova, sending a shock wave rippling outward. That disturbance caused the cloud to collapse inward, pulled by its own gravity. And from that collapse, over millions of years, our sun was born at the center, with the planets slowly accreting from the leftover material spinning around it. The whole system came together not through chaos, but through the patient mathematics of gravity and motion. The sun contains 99.86% of all the mass in our solar system. Everything else, all 8 planets, all the moons, all the asteroids, all the comets, all the dust, all of it combined makes up just 0.14%. We live in a system utterly dominated by one object. The sun is so massive that even Jupiter, the largest planet, is barely 1,000th of the sun's mass. It's humbling, really. All our stories, all our history, all our concerns happen on a tiny world orbiting a star that could swallow 1 million Earths. And yet, here we are. Conscious, thinking about it. Mercury is the closest planet to the sun, orbiting at an average distance of about 36 million miles. That's close, cosmically speaking. Close enough that temperatures on Mercury's surface can reach 800 degrees Fahrenheit during the day. But here's what's strange. Despite being the nearest planet to our star, Mercury isn't the hottest planet in the solar system. That title goes to Venus, which we'll get to shortly. Mercury has almost no atmosphere to trap heat, so when night falls on Mercury, which lasts for 88 Earth days, temperatures plummet to minus 290 degrees Fahrenheit. Imagine that swing, from baking to freezing on the same small world. Mercury is also the smallest planet in our solar system since Pluto was reclassified in 2006. Mercury is only slightly larger than Earth's moon, You could fit Mercury inside Earth about 18 times. Despite its small size, Mercury is the second densest planet after Earth. That density comes from its enormous iron core, which makes up about 85% of the planet's radius. Scientists believe Mercury might have once been larger, but a massive collision in the early solar system stripped away much of its rocky mantle, leaving behind a world that's mostly just core and a thin shell. A cosmic accident that left Mercury exposed, vulnerable, dense. One day on Mercury, a full rotation on its axis, takes 59 Earth days. But 1 year on Mercury, one complete orbit around the Sun, takes only 88 Earth days. This creates a strange situation. If you were standing on Mercury's surface, you'd experience 2 sunrises per Mercurian year. The sun would rise, then appear to reverse and set again before finally rising once more. This happens because of Mercury's elliptical orbit and its slow rotation combining in peculiar ways. Time works differently there, measured by a clock that seems to stutter and pause. The universe has its own rhythms, stranger than ours. Venus is the second planet from the Sun, orbiting at about 67 million miles out. It's often called Earth's twin because the 2 planets are nearly identical in size and mass. Venus is only about 5% smaller than Earth, but that's where the similarities end. Venus is a hellscape, a world that went terribly wrong somewhere in its history. The surface temperature on Venus averages around 870 degrees Fahrenheit, hot enough to melt lead. This makes Venus the hottest planet in the solar system, despite being nearly twice as far from the Sun as Mercury. The reason is Venus's atmosphere. Venus has an atmosphere that's 92 times denser than Earth's. That's the pressure you'd experience if you dove about 3,000 feet below the ocean's surface here on Earth. And Venus's atmosphere is 96% carbon dioxide, creating a runaway greenhouse effect. Heat from the sun gets trapped beneath those thick clouds and can't escape. The clouds themselves are made of sulfuric acid, raining down in some regions, but evaporating before reaching the surface. It's a world of eternal twilight beneath those clouds, where the wind howls at 200 miles per hour in the upper atmosphere. No probe humanity has landed there has survived more than a few hours. Venus rotates on its axis incredibly slowly and in the opposite direction from most planets. We call this retrograde rotation. One day on Venus, one complete spin takes 243 Earth days. But 1 year on Venus, one orbit around the Sun takes only 225 Earth days. This means a day on Venus is actually longer than a year on Venus. Think about that. You'd celebrate a birthday before you'd see a single sunrise and sunset. And because of that retrograde rotation, the sun would rise in the west and set in the east, if you could see it through those clouds. Time again, playing by different rules. Earth is the third planet from the Sun, orbiting at an average distance of 93 million miles. We call this distance 1 astronomical unit, or AU, and we use it as a measuring stick for the solar system. Earth is the largest of the rocky planets and the only world we know of that harbors life. Our planet is about 71% water, which gives us those beautiful blue swirls when seen from space. That water, combined with our atmosphere and our distance from the sun, creates conditions where liquid water can exist on the surface. And where there's liquid water, there's the possibility of life as we know it. Earth has one moon, which we simply call the moon. It's the fifth largest moon in the solar system, about 1/4 the diameter of Earth. The moon formed roughly 4.5 billion years ago, likely from debris kicked up when a Mars-sized object crashed into the early Earth in what scientists call the giant impact hypothesis. That collision was so violent it melted and vaporized rock, sending huge amounts of material into orbit around Earth. Over time, that material coalesced into our moon. From catastrophe, a companion was born. The moon is slowly drifting away from Earth at a rate of about 1.5 inches per year. Scientists know this because astronauts from the Apollo missions left reflectors on the moon's surface, and we bounced lasers off them to measure the distance precisely. 1.5 inches doesn't sound like much, but over billions of years, it adds up. Billions of years ago, the moon was much closer, and it appeared much larger in Earth's sky. The tides it created were enormous, hundreds of feet high, reshaping coastlines with every cycle. Slowly, our companion pulls away into the dark. Earth's day is 24 hours long, which we all know intimately, but that length isn't constant. Earth's rotation is gradually slowing down due to tidal forces from the moon. About 600 million years ago, a day on Earth was only about 22 hours long. And in the far future, billions of years from now, Earth's day will lengthen to the point where one side always faces the moon, just as one side of the moon always faces Earth now. But that's so far in the future, the sun will likely have expanded into a red giant by then. Even our most familiar rhythms are temporary. Mars is the fourth planet from the sun, orbiting at about 142 million miles, or 1.5 AU. Mars is about half the diameter of Earth, making it the second smallest planet after Mercury. Mars is often called the red planet because of the iron oxide, essentially rust, that covers its surface. That rust gives Mars its distinctive reddish color, visible even to the naked eye from Earth. Ancient civilizations named it after their gods of war because of that blood-red hue. A rusty world colored by time and chemistry. Mars has two small moons, Phobos and Deimos. Their names mean fear and dread in Greek, the companions of Ares, the Greek god of war. Phobos is the larger of the two, about 14 miles across at its widest point. It orbits so close to Mars that it completes an orbit in just 7.5 hours. From Mars's surface, you'd see Phobos rise in the west and set in the east multiple times per day. Phobos is also slowly spiraling inward toward Mars. In about 50 million years, it will either crash into the surface or break apart into a ring. Even moons have expiration dates. Mars has the largest volcano in the solar system, Olympus Mons. This shield volcano rises about 13.5 miles above the surrounding plains. That's nearly 2.5 times the height of Mount Everest. Olympus Mons is so large that if you stood on its summit, you couldn't see the edges because they'd curve below the horizon. And if you stood at its base, you couldn't see the peak because of the planet's curvature. It's a volcano the size of the state of Arizona. It formed over billions of years because Mars lacks plate tectonics. On Earth, volcanic hotspots move as our tectonic plates shift. But on Mars, the hotspot stays in one place, building up and up and up, a mountain built by patience and stillness. Mars also has the solar system's largest canyon system, Valles Marineris. This enormous crack in Mars's surface stretches about 2,500 miles long, up to 430 miles wide in places, and reaches depths of 4 miles. If you placed Valles Marineris on Earth, it would stretch from New York to Los Angeles. The Grand Canyon would fit in seats many times over. Scientists aren't entirely sure how Valles Marineris formed. It might have been created by the cooling and cracking of the planet's crust, or by ancient tectonic activity, or by water erosion billions of years ago. A scar across a world, or telling a story we're still learning to read. Mars has seasons, just like Earth. This is because Mars's axis is tilted at about 25 degrees, very similar to Earth's 23.5 degrees. But because Mars's year is 687 Earth days long, each season on Mars lasts about twice as long as seasons on Earth. Mars also has polar ice caps made of water ice and frozen carbon dioxide, also called dry ice. These ice caps grow and shrink with the seasons. In the Martian winter, carbon dioxide from the atmosphere freezes and falls as snow, building up the ice caps. In summer, that frozen carbon dioxide sublimates, turning directly from solid to gas, and the ice caps shrink. A world with rhythms that mirror our own, but stretched out, slowed down. Between Mars and Jupiter lies the asteroid belt, a region of space containing millions of rocky objects. These asteroids are remnants from the early solar system, material that never coalesced into a planet because of Jupiter's gravitational influence. The largest object in the asteroid belt is Ceres, which is about 580 miles in diameter. Ceres is so large, it's classified as a dwarf planet. The asteroid belt sounds crowded, but space is vast. If you were traveling through the asteroid belt, you likely wouldn't see another asteroid even with a telescope. They're spread out over an enormous volume, space giving each rock its own loneliness. Jupiter is the 5th planet from the Sun and the largest planet in our solar system. It orbits at about 484 million miles, or 5.2 AU from the Sun. Jupiter is a gas giant, meaning it has no solid surface. It's made mostly of hydrogen and helium, the same stuff as stars. Jupiter is so large that you could fit all the other planets in the solar system inside it with room to spare. You could fit 1,300 Earths inside Jupiter. Its mass is 2.5 times greater than all the other planets combined. A giant among worlds, holding court in the outer darkness. Jupiter's most famous feature is the Great Red Spot, a massive storm that's been raging for at least 350 years, possibly much longer. We've been observing it since the 1600s. The Great Red Spot is an anticyclone, a high-pressure region where winds swirl in the opposite direction from a hurricane. At its widest, the storm measures about 10,000 miles across. That means you could fit 2 or 3 Earths side by side inside it. The storm's winds reach speeds of about 270 miles per hour at its edges, and it's slowly shrinking. Observations over the past century show the Great Red Spot getting smaller, though scientists aren't sure why. A storm older than nations, slowly fading. Jupiter has at least 95 known moons, and probably more waiting to be discovered. 4 of these moons are particularly large and bright. They're called the Galilean moons because Galileo Galilei discovered them in 1610. Their names are Io, Europa, Ganymede, and Callisto. These moons are large enough that you can see them with binoculars from Earth. In fact, Galileo discovered them with a telescope less powerful than cheap binoculars today. Watching these moons orbit Jupiter night after night convinced Galileo that not everything in the heavens orbited Earth. It was revolutionary. 4 moons that changed how we see our place in the cosmos. Io is the innermost of the Galilean moons, and it's the most volcanically active body in the solar system. Io has over 400 active volcanoes. Some of these volcanoes spew lava fountains up to 250 miles high, far above the surface. There's no atmosphere to speak of, so these volcanic plumes shoot straight up in graceful arcs before falling back down. Io's intense volcanism is caused by tidal heating. Jupiter's immense gravity, along with the gravitational tugs from Europa and Ganymede, constantly squeezes and stretches Io. This friction generates enormous heat inside the moon, keeping it molten and active. A world in constant agony, pulled apart by giants. Europa is the second Galilean moon, and it's one of the most intriguing objects in the solar system. Europa is covered in a thick shell of water ice, crisscrossed with dark linear features that scientists call lineae. These cracks and ridges suggest that the ice shell is constantly shifting and breaking. Beneath that ice, scientists believe there's a global ocean of liquid water kept warm by tidal heating from Jupiter. This ocean might contain twice as much water as all of Earth's oceans combined. And where there's liquid water, there's the possibility of life. NASA is planning missions to Europa to search for signs of biology in that hidden ocean, a moon that might harbor life beneath a frozen shell orbiting a giant. Ganymede is the largest moon in the solar system, even larger than the planet Mercury. Ganymede has a diameter of about 3,273 miles. It's the only moon known to have its own magnetic field, which suggests it has a liquid iron core deep inside. Like Europa, Ganymede probably has a subsurface ocean beneath its icy crust. Scientists have detected auroras around Ganymede, shimmering lights caused by charged particles interacting with its magnetic field. It's strange to think of auroras on a moon, but there they are, dancing in the darkness. Even moons can have magnetic personalities. Callisto is the outermost of the 4 Galilean moons. It's the most heavily cratered object in the solar system, meaning its surface is ancient and largely unchanged for billions of years. Callisto doesn't experience the same tidal heating as Io and Europa because it's farther from Jupiter. It's a quiet world, geologically dead, simply holding onto the scars of its violent youth. But even Callisto might have a subsurface ocean detected through subtle changes in its magnetic field, as measured by spacecraft. If Callisto has an ocean, it's much deeper and colder than Europa's, buried under 100 miles of ice and rock, a frozen archive of impacts, hiding its own secrets. Jupiter also has rings, though they're much fainter than Saturn's. Jupiter's rings are made mostly of dust particles kicked up when small meteoroids crash into Jupiter's inner moons. These dust particles are so fine and dark that they weren't discovered until 1979, when Voyager 1 flew past Jupiter and looked back toward the Sun, seeing the rings backlit. From Earth, Jupiter's rings are nearly impossible to see. But they're there, a faint halo around the giant, constantly replenished by collisions. Even the king of planets wears a crown, however humble. Saturn is the 6th planet from the Sun, orbiting at about 886 million miles, or 9.5 AU. Saturn is the 2nd largest planet in the solar system, but it's also the least dense. In fact, Saturn is less dense than water. If you could find an ocean large enough, Saturn would float. Of course, no such ocean exists, but it's a striking thought. Saturn, like Jupiter, is a gas giant made mostly of hydrogen and helium. High in Saturn's atmosphere, winds reach speeds of 1,100 miles per hour, some of the fastest winds in the solar system. A giant so light it could float, wrapped in furious winds. Saturn is, of course, famous for its rings. These rings extend outward from the planet for about 175,000 miles, but they're remarkably thin. The main rings are only about 30 feet thick in most places. If you made a scale model of Saturn's rings using paper, the paper would be thousands of times too thick. The rings are made of countless particles of ice and rock, ranging in size from tiny grains to house-sized boulders. These particles orbit Saturn independently, each following its own path, collectively creating the appearance of solid rings, a disk of shattered moonlets, forever circling. Scientists aren't entirely sure how Saturn's rings formed. One hypothesis suggests they're the remnants of a moon that wandered too close to Saturn and was torn apart by tidal forces. Another idea is that the rings are leftover material from Saturn's formation that never coalesced into moons. Recent data from the Cassini spacecraft, which orbited Saturn from 2004 to 2017, suggests the rings might be relatively young, perhaps only 100 million years old. That's young, cosmically speaking. The dinosaurs had already come and gone by then. Saturn might not have had its rings for most of its existence. Beauty, arriving late in the story. Saturn has at least 146 known moons, more than any other planet. Most are small, irregular chunks of rock and ice, but several are quite large and scientifically interesting. The largest is Titan, Saturn's most intriguing moon. Titan is the second largest moon in the solar system after Ganymede, and the only moon with a thick atmosphere. Titan's atmosphere is denser than Earth's, made mostly of nitrogen with some methane and other hydrocarbons. This atmosphere gives Titan a hazy orange appearance. You can't see the surface through those clouds without radar. A moon with an atmosphere thicker than ours, hiding its face. Titan's surface is cold, with temperatures around minus 290 degrees Fahrenheit. At those temperatures, water ice is as hard as rock. But Titan has lakes and rivers and rain, not of water, but of liquid methane and ethane. Titan is the only place besides Earth where we've confirmed stable bodies of liquid on the surface. These hydrocarbon lakes mostly cluster near Titan's poles. The largest, Kraken Mare, is bigger than the Caspian Sea. Imagine that. A moon with a weather cycle where methane evaporates, forms clouds, and rains back down, carving channels and filling lakes. A hydrological cycle written in alien chemistry. Saturn's moon Enceladus is small, only about 310 miles in diameter, but it's one of the brightest objects in the solar system because its surface is covered in fresh, clean ice. Enceladus reflects nearly 100% of the sunlight that hits it. But the real discovery came in 2005, when the Cassini spacecraft photographed enormous plumes of water vapor and ice particles erupting from cracks near Enceladus's south pole. These plumes shoot hundreds of miles into space. They come from a subsurface ocean beneath the ice, kept liquid by tidal heating. The plumes contain organic molecules and salts, suggesting hydrothermal activity on the ocean floor. A tiny moon, spraying its ocean into space for us to sample. Uranus is the seventh planet from the Sun, orbiting at about 1.8 billion miles, or 19 AU. Uranus is an ice giant, smaller than Jupiter and Saturn, but still much larger than Earth. Uranus has a diameter about 4 times Earth's. What makes Uranus unique is its axial tilt. Most planets spin roughly upright as they orbit the Sun, maybe tilted a bit like Earth's 23 degrees. But Uranus is tilted 98 degrees. It essentially rolls around the Sun on its side. Scientists think a massive collision early in the solar system's history knocked Uranus over. A world that tumbles rather than spins, knocked sideways long ago. Because of its extreme tilt, Uranus has the most extreme seasons in the solar system. Each pole gets about 42 years of continuous sunlight, followed by 42 years of continuous darkness. Imagine living through a summer or winter that lasts 4 decades. The planet's atmosphere is made mostly of hydrogen and helium, with some methane. That methane gives Uranus its blue-green color because methane absorbs red light and reflects blue. Uranus is so far from the Sun that it receives only 1/400th the sunlight that Earth does. It's a cold, dim world, a frozen giant rolling through its long, lonely seasons. Uranus has 27 known moons, all named after characters from the works of William Shakespeare and Alexander Pope. The largest moons are Miranda, Ariel, Umbriel, Titania, and Oberon. Miranda is particularly interesting because its surface looks like it was assembled from mismatched pieces. Miranda has enormous cliffs, some as high as 3 miles, towering over jumbled terrain. Scientists think Miranda might have been shattered by an impact early in its history and then reassembled under its own gravity, creating a patchwork surface. A moon that broke and came back together, wearing its scars. Uranus also has rings, though they're dark and difficult to see. The rings were discovered in 1977 when astronomers watched Uranus pass in front of a star. For the planet itself blocked the star blinked on and off several times. Those blinks were the rings passing in front of the star. Uranus's rings are narrow and widely spaced, made of dark particles that might be organic compounds processed by radiation. 13 rings have been identified so far. They're not as spectacular as Saturn's, but they're there, circling the tilted giant. Another ring system found by watching light disappear and return. Neptune is the 8th and outermost planet in our solar system, orbiting at about 2.8 billion miles, or 30 AU from the Sun. Neptune is slightly smaller than Uranus, but more massive. It's another ice giant with a similar composition. Neptune's atmosphere is also blue, but a deeper, richer blue than Uranus. This deeper color might be caused by an unknown compound in Neptune's atmosphere. Like the other giant planets, Neptune is mostly hydrogen and helium, with ice of water, methane, and ammonia deeper down. The most distant world, wrapped in the deepest blue. Neptune has the fastest winds in the solar system, with speeds reaching up to 1,200 miles per hour. That's faster than the speed of sound on Earth. These supersonic winds scream around the planet in the opposite direction of Neptune's rotation. Scientists aren't sure what drives these winds. Neptune receives very little energy from the Sun at its distance, yet it radiates more than twice as much energy as it receives. This suggests Neptune has an internal heat source, perhaps leftover heat from its formation, slowly leaking out and driving those ferocious winds. A world heating itself from within, wearing a cloak of violent wind. Neptune's largest moon is Triton, one of the strangest moons in the solar system. Triton is the only large moon with a retrograde orbit, meaning it orbits Neptune in the opposite direction from Neptune's rotation. This tells scientists that Triton wasn't formed around Neptune. Instead, Triton was likely a dwarf planet from the Kuiper Belt that Neptune captured with its gravity. Triton is slowly spiraling inward toward Neptune. In about 3.6 billion years, it will pass inside Neptune's Roche limit, the distance at which tidal forces will tear it apart. Triton will become a ring system around Neptune, a captured moon doomed, falling inward across billions of years. Triton is geologically active despite being so far from the Sun. When Voyager 2 flew past in 1989, it photographed geysers of nitrogen erupting from Triton's surface, shooting material up to 5 miles high. Triton's surface temperature is about -390 degrees Fahrenheit, making it one of the coldest places we've measured in the solar system. Yet somehow there's enough internal heat to drive those nitrogen geysers. Triton's surface is young, meaning it's been resurfaced relatively recently by geological activity. It's covered in a pinkish ice that might be nitrogen or methane ice mixed with organic compounds. A frozen moon, still restless, still erupting. Beyond Neptune lies the Kuiper Belt, a vast region of space filled with icy bodies left over from the solar system's formation. The Kuiper Belt extends from about 30 AU to around 50 AU from the Sun. It's similar to the asteroid belt, but much larger and much farther out. The objects in the Kuiper Belt are often called Kuiper Belt objects, or KBOs. They're made mostly of frozen volatiles like methane, ammonia, and water ice. Thousands of KBOs have been discovered, and there are likely hundreds of thousands more waiting to be found. A frozen frontier littered with the solar system's building blocks. The most famous former planet, Pluto, resides in the Kuiper Belt. Pluto orbits the Sun at an average distance of about 3.7 billion miles, or 39 AU. Pluto was discovered in 1930 by Clyde Tombaugh and was considered the 9th planet for 76 years. Then in 2006, the International Astronomical Union redefined what it means to be a planet. Pluto didn't make the cut because it hasn't cleared its orbital neighborhood of other debris. So Pluto was reclassified as a dwarf planet. Many people felt sad about this. Pluto was demoted in a sense, but Pluto itself doesn't mind. It's still there, still orbiting, still fascinating. A world we once called planet, still itself regardless of names. Pluto has 5 known moons. The largest, Charon, is so big relative to Pluto that the two are often considered a binary system. Charon is about half Pluto's diameter. Pluto and Charon are tidally locked to each other, meaning the same sides always face each other as they orbit their common center of mass. If you stood on the Pluto-facing side of Charon, you'd always see Pluto in the same spot in the sky. And if you stood on the Charon-facing side of Pluto, Charon would hover overhead forever. The other 4 moons, Styx, Nix, Kerberos, and Hydra, are much smaller. 2 worlds forever facing each other, dancing in the dark. In 2015, NASA's New Horizons spacecraft flew past Pluto, giving us our first close-up look at this distant world. The images revealed a complex, varied surface. Pluto has mountains made of water ice rising 2 miles high. It has a vast plain called Sputnik Planitia that appears to be frozen nitrogen, smooth and crater-free, suggesting recent geological activity. Pluto has an atmosphere, thin but present, made mostly of nitrogen that slowly escapes into space. Pluto even has a faint blue haze in its atmosphere, created when sunlight breaks apart methane molecules. A dwarf planet, revealed as beautiful and complex and alive. Pluto's surface features are named after underworld deities, explorers, scientists, and pioneers, as well as fictional explorers and underworld locations. So you have regions named after Cthulhu, Balrog, and Sleipnir. There's a plain informally called Tombaugh Regio, honoring Pluto's discoverer. These names give Pluto a mythology all its own, a fitting end to the known planets in the beginning of the unknown beyond. Names from myth and fiction given to a world at the edge. Beyond the Kuiper Belt lies the scattered disk, a region of space where objects have highly elliptical and inclined orbits. These scattered disk objects were likely flung outward by gravitational interactions with Neptune early in the solar system's history. Some of these objects have orbits that take them hundreds of AU from the Sun. The dwarf planet Eris, discovered in 2005, is one such object. Eris is about the same size as Pluto and is one of the most massive dwarf planets known. Its discovery was one of the catalysts for the debate that led to Pluto's reclassification. Distant worlds scattered by the giant planets, wandering far. Even farther out lies the Oort cloud, a theoretical shell of icy objects surrounding the solar system. The Oort cloud is thought to extend from about 2,000 AU to as far as 100,000 AU from the Sun, maybe farther. That's nearly 2 light years away, halfway to the nearest star. The Oort cloud has never been directly observed. We infer its existence from the long-period comets that occasionally fall into the inner solar system. These comets have orbital periods measured in thousands or even millions of years. They must come from somewhere far away, and the Oort cloud is the best explanation. A cloud of potential comets surrounding us at distances we can barely imagine. Comets are often described as dirty snowballs. They're made of ice, dust, and rocky material. When a comet's orbit brings it close to the sun's heat causes the ice to sublimate, turning directly from solid to gas. This creates the comet's coma, a fuzzy envelope of gas and dust around the nucleus, and its tail, which always points away from the sun because of solar wind and radiation pressure. Comets can have 2 tails, a dust tail that curves slightly, and an ion tail that points straight away from the sun. Some comets are ancient, pristine samples of the material that formed the solar system billions of years ago. Messengers from the outer dark, revealing themselves only in the sun's light. One of the most famous comets is Halley's Comet, which returns to the inner solar system every 75 to 76 years. It was named after Edmund Halley, who calculated its orbit and predicted its return. Halley's Comet has been observed and recorded for thousands of years. Ancient Chinese astronomers recorded it as early as 240 BCE. It appeared in the Bayeux Tapestry, commemorating its sighting in 1066 before the Norman Conquest. Mark Twain was born shortly after its appearance in 1835 and said he expected to go out with it. He died in 1910, just as it returned. Halley's Comet last visited in 1986 and will return in 2061. A cosmic clock marking human history with each bright return. Let's talk about the Sun itself, the heart of our system. The Sun is a G-type main sequence star, what astronomers classify as a yellow dwarf, though it actually appears white from space. Earth's atmosphere scatters the sunlight, making it look more yellow to us. The Sun is about 4.6 billion years old, roughly halfway through its main sequence lifetime. In another 5 billion years, the Sun will exhaust its hydrogen fuel and begin fusing helium. It will swell into a red giant, possibly engulfing Mercury, Venus, and even Earth. But that's a long time from now. For now, the Sun burns steadily. Our star, middle-aged, stable, life-giving. The Sun's core temperature is about 15 million degrees Celsius. At those temperatures and under immense pressure, hydrogen nuclei fuse together to form helium, releasing enormous amounts of energy. This energy takes thousands of years to travel from the core to the Sun's surface, bouncing around as photons get absorbed and re-emitted countless times. But once energy reaches the surface, it travels as light and takes only 8 minutes and 20 seconds to reach Earth. That means when you look at the Sun, you're seeing it as it was 8 minutes ago. The light that warms your face left the Sun before you looked up. The Sun rotates, but not as a solid body. Different latitudes rotate at different speeds because the Sun is made of plasma. At the equator, the Sun rotates once every 25 days. Near the poles, it takes about 35 days. This differential rotation creates tangles in the Sun's magnetic field, which can lead to sunspots, solar flares, and coronal mass ejections. These phenomena follow an 11-year cycle. Solar maximum brings lots of sunspot activity, while solar minimum is quieter. We're currently in solar cycle 25, which began in 2019. The Sun, restless, tangling its own magnetic field. Sunspots are temporary darker regions on the Sun's surface caused by magnetic activity. They appear dark because they were cooler than the surrounding areas, though they're still about 6,500 degrees Fahrenheit. Some sunspots are larger than Earth. They can last for weeks before fading away. Ancient Chinese astronomers observed sunspots as early as 800 BCE, though European scientists didn't systematically study them until Galileo's time. For a while, some people thought sunspots were small planets passing in front of the Sun. But no, they're features on the Sun itself. Dark patches on a blazing star, each one larger than our world. Solar flares are sudden, intense bursts of radiation from the Sun. They happen when magnetic energy built up in the solar atmosphere is suddenly released. A solar flare can release as much energy as billions of nuclear bombs detonating simultaneously. Flares are classified by their X-ray brightness, from class small to M class, medium, to X class, large. The most powerful flares can disrupt radio communications on Earth and can be hazardous to astronauts in space. Fortunately, Earth's atmosphere and magnetic field protect us on the surface. The Sun occasionally erupting, reminding us of its power. Coronal mass ejections, or CMEs, are huge bubbles of plasma and magnetic field ejected from the Sun. They can contain billions of tons of material traveling at millions of miles per hour. When a CME reaches Earth, it can cause geomagnetic storms that disrupt satellites, power grids, and communication systems. But CMEs also create beautiful auroras, the northern and southern lights, when charged particles interact with Earth's magnetic field and atmosphere. The most powerful geomagnetic storm on record, the Carrington event of 1859, caused auroras visible as far south as the Caribbean and disrupted telegraph systems worldwide. Beauty and danger arriving together from the sun. The sun produces a constant stream of charged particles called the solar wind. This wind flows outward in all directions, traveling at about 1 million miles per hour. The solar wind reaches the edge of the solar system, where it eventually slows and blends with the interstellar medium. The boundary where the solar wind meets interstellar space is called the heliopause. Voyager 1 became the first human-made object to cross the heliopause in 2012. It's now in interstellar space, still transmitting data back to Earth from over 14 billion miles away. Our farthest ambassador, sailing beyond the sun's reach, the solar wind shapes Earth's magnetic field into a teardrop shape called the magnetosphere. On the side facing the sun, the magnetosphere is compressed to about 6 Earth radii. On the night side, it stretches out into a long tail called the magnetotail, extending millions of miles into space. The magnetosphere protects us from the solar wind. Without it, the solar wind would slowly strip away Earth's atmosphere, as it's done to Mars. Mars lost most of its atmosphere billions of years ago when its magnetic field shut down. Earth's magnetic field is a shield we rarely think about, but it's essential for life, an invisible barrier standing between us and the stellar wind. Earth's magnetic field is generated by the motion of molten iron in the planet's outer core. This process is called the geodynamo. The magnetic field isn't static, it wanders and changes over time. Right now, magnetic north is drifting from Canada towards Siberia at about 34 miles per year, and occasionally the field reverses completely. North becomes south and south becomes north. These reversals happen irregularly, roughly every few 100,000 years on average. The last reversal was 780,000 years ago. We're overdue, and it's as though overdue doesn't really apply to chaotic processes. Our planet's magnetic heart, restless, wandering, occasionally flipping. Let's return to the planets and talk about their tilts, their axial tilts, which determine their seasons. Mercury has almost no tilt, just 0.03 degrees. This means Mercury has virtually no seasons. Venus is tilted 177 degrees, which means it's nearly upside down. Combined with its retrograde rotation, Venus is a world turned on its head. Earth's 23.5-degree tilt gives us our familiar seasons. Mars's 25-degree tilt creates seasons similar to Earth's. Jupiter and Saturn have tilts of about 3 and 27 degrees respectively. Each world tips at its own angle, creating its own rhythm of light and dark. The planets all orbit the sun in roughly the same plane, called the ecliptic. This is because they all formed from the same rotating disk of gas and dust. If you look at the solar system from above the sun's north pole, all the planets orbit counterclockwise. Mercury completes an orbit in 88 days. Earth takes 365 days. Neptune takes 165 years. The outer planets move slowly in their vast orbits. Since Neptune was discovered in 1846, it has completed less than 2 full orbits. It won't complete its second orbit since discovery until 2011. time measured differently at different distances from the sun. The planets also vary in density. The rocky inner planets, Mercury, Venus, Earth, and Mars, are dense. Earth is the densest, with an average density about 5.5 times that of water. The gas giants, Jupiter and Saturn, are much less dense. Saturn, as we mentioned, would float in water. The ice giants, Uranus and Neptune, are denser than the gas giants, but less dense than the rocky planets. This variation reflects their composition. The inner planets are mostly rock and metal. The outer planets are mostly hydrogen, helium, and ices. Different recipes for different worlds, sorted by distance from the sun. Orbital resonances are common in the solar system. These happen when two orbiting bodies exert regular, periodic gravitational influence on each other, usually because their orbital periods are related by a ratio of small integers. For example, Neptune and Pluto are in a 3:2 resonance. For every 3 orbits Neptune makes, Pluto makes 2. This resonance actually protects Pluto from getting too close to Neptune, even though their orbits cross when viewed from above. Many of Jupiter's moons are in resonances with each other. Io, Europa, and Ganymede are in a 4:2:1 resonance, often called the Laplace resonance. Orbits locked in mathematical ratios, dancing in synchrony. Tidal locking is another common phenomenon. It happens when an object's orbital period matches its rotational period, so the same side always faces the object it's orbiting. Our moon is tidally locked to Earth. We always see the same face of the moon. The far side, often incorrectly called the dark side, wasn't photographed until the Soviet Luna 3 probe in 1959. Many moons in the solar system are tidally locked to their planets. Even Mercury is in a unique tidal lock with the Sun, rotating 3 times for every 2 orbits. Gravity, gently insisting that some faces always meet. Let's talk about the colors of the planets. Mercury is gray, covered in ancient, rocky terrain that resembles our moon. Venus is shrouded in yellow-white clouds of sulfuric acid, hiding its surface. Earth is blue and white, water and clouds. Mars is red from iron oxide. Jupiter is tan with brown, white, and red bands created by clouds at different altitudes. Saturn is pale gold, with subtler banding than Jupiter. Uranus is cyan, and Neptune is a deeper blue. These colors tell us about the chemistry and weather of each world. Each planet wearing its own hue, painted by its atmosphere and surface. The fastest rotation in the solar system belongs to Jupiter. Despite being the largest planet, Jupiter rotates once every 9 hours and 55 minutes. This rapid rotation creates Jupiter's distinctive banded appearance, with winds separating into zones and belts at different latitudes. The rapid spin also causes Jupiter to bulge at the equator. Jupiter's equatorial diameter is about 7% larger than its polar diameter. You can see this flattening in good photographs of the planet, a giant spinning so fast it swells at its middle. The slowest rotation belongs to Venus, taking 243 Earth days to spin once. If you could stand on Venus's surface and survive the heat and pressure, you'd experience a day that lasts longer than a year. The sun would creep across the sky at an almost imperceptible pace. Venus's slow rotation might be due to tidal interactions with the sun and atmospheric friction, though the exact reason remains uncertain. A world that turns so slowly, time seems to pause. Some moons in the outer solar system show evidence of past or present subsurface oceans. Europa, Ganymede, Callisto, Enceladus, and Titan all fall into this category. These oceans exist because of tidal heating, chemical composition, and internal radioactive decay, keeping the interiors warm enough for liquid water despite being so far from the sun. The discovery of these potential oceans has revolutionized our thinking about where life might exist. Life, as we know it, requires liquid water. If multiple moons have oceans, then the solar system has far more potentially habitable real estate than we once thought. Hidden seas on distant moons, expanding the boundaries of possibility. The tallest mountain in the solar system, as we mentioned, is Olympus Mons on Mars. But the deepest canyon isn't Valles Marineris. The deepest known canyon in the solar system is on Vesta, one of the largest asteroids in the asteroid belt. Vesta has a canyon near its south pole that's about 12 miles deep. The South Pole itself shows signs of a massive impact that nearly shattered Vesta. This impact created a central peak taller than Olympus Mons. Vesta is a world of extremes, considering it's only about 326 miles in diameter. Even small worlds can have grand topography. The coldest place in the solar system isn't at its edge. It's in permanently shadowed craters near the moon's south pole, where temperatures drop to about minus 400 degrees Fahrenheit, colder than Pluto's average temperature. These craters never receive sunlight. Any water ice or other volatile materials that wander into these cold traps stay frozen for billions of years. NASA's Lunar Reconnaissance Orbiter has detected water ice in these shadowed regions. Future lunar bases might mine this ice for drinking water and rocket fuel. Cold traps on our nearest neighbor, preserving ancient ice. Speaking of water, there's more water in the solar system than just on Earth. Europa might have twice as much water as Earth. Enceladus has a global ocean. Ganymede and Callisto likely have subsurface oceans. Even tiny Ceres, the dwarf planet in the asteroid belt, might have a subsurface ocean, or at least pockets of liquid water. Comets are mostly ice. Many asteroids contain water locked in minerals. The total amount of water in the solar system is staggering. Earth's oceans are just one drop in a vast cosmic reservoir. Water scattered across the system, hiding in moons and icy wanderers. The asteroid belt isn't the only source of small bodies. Near-Earth asteroids occasionally cross Earth's orbit. Some of these asteroids are potentially hazardous, meaning they could collide with Earth. Scientists catalog these objects and calculate their orbits to predict close approaches. In 2013, a small asteroid about 65 feet in diameter entered Earth's atmosphere over Chelyabinsk, Russia. It exploded in an airburst, releasing energy equivalent to about 500 kilotons of TNT. The shock wave injured over 1,000 people, mostly from broken glass. It was a reminder that space isn't empty and impacts still happen. The sky occasionally reminding us that it's not empty. NASA and other space agencies are developing plans to deflect asteroids if one is found on a collision course with Earth. In 2022, NASA's DART mission successfully changed the orbit of a small asteroid moon called Dimorphos by crashing a spacecraft into it. This was the first test of planetary defense technology. It worked. The impact altered Dimorphos's orbit around its parent asteroid, proving that kinetic impactors can deflect asteroids. It's reassuring to know we're developing the ability to protect ourselves. Humanity learning to nudge rocks in space. The planets produce their own magnetic fields to varying degrees. Earth and Jupiter have strong magnetic fields. Saturn, Uranus, and Neptune have weaker but still substantial fields. Mars, Venus, and Mercury have weak or no global magnetic fields, though Mars has localized crustal magnetic fields, remnants of an ancient global field. Magnetic fields are generated by the motion of conductive materials inside a planet. For Earth, it's molten iron in the outer core. For Jupiter, it might be metallic hydrogen deep in the interior. The presence or absence of a magnetic field affects a planet's atmosphere and ability to retain it against the solar wind. Invisible fields, shaping the space around worlds. Jupiter's magnetic field is the strongest in the solar system, about 20,000 times stronger than Earth's. It extends so far into space that if we could see it from Earth, it would appear larger than the Fullmond in our Skimmingen. Jupiter's magnetosphere traps charged particles, creating intense radiation belts that are hazardous to spacecraft. The Juno spacecraft, which has been orbiting Jupiter since 2016, has to follow carefully planned orbits to minimize its radiation exposure. Even so, Juno's electronics are hardened against radiation, and the mission is expected to end when the radiation finally destroys the spacecraft's systems. A magnetic giant filling space with its dangerous embrace. Some asteroids have their own moons. These are called binary asteroids. About 16% of near-Earth asteroids are thought to be binary or even triple systems. The asteroid Ida, visited by the Galileo spacecraft in 1993, was the first asteroid discovered to have a moon. Ida's moon, Dactyl, is tiny, only about a mile across, but it orbits Ida just as moons orbit planets. Even some Kuiper Belt objects have moons. Pluto, as we mentioned, has 5. The Kuiper Belt object MK2, nicknamed Makemake, has at least 1 moon. In the outer solar system, binary objects are common. Even asteroids have companions, orbiting each other in the dark. The heliosphere is the bubble of space dominated by the sun's solar wind. It extends well beyond the planets, out past the Kuiper Belt. The edge of the heliosphere, the heliopause, is where the solar wind pressure balances with the pressure of the interstellar medium. Voyager 1 and Voyager 2 have both crossed the heliopause and are now in interstellar space. Data from the Voyager spacecraft have revealed that the heliopause isn't smooth but irregular, rippling like a flag in the wind as the solar wind strength varies and as the sun moves through the galaxy. The sun's influence extending billions of miles but finally ending. Our solar system is moving through the galaxy at about 500,000 miles per hour relative to the cosmic microwave background. We're orbiting the center of the Milky Way galaxy, which lies about 26,000 light years away. It takes solar system about 230 million years to complete one orbit around the galaxy. This is sometimes called a cosmic year. Since the sun formed, it has completed about 20 orbits. The last time the solar system was in its current galactic position, dinosaurs were just beginning to diversify on Earth. We're on a grand journey around the galaxy, slow and vast. The planets occasionally align in interesting configurations. A planetary conjunction occurs when 2 or more planets appear close together in Earth's sky. These are purely line-of-sight effects. The planets aren't actually near each other in space. They just happen to lie in the same direction from Earth's perspective. In December of 2020, Jupiter and Saturn appeared so close together they were almost touching, the closest conjunction since 1623. Such events are sometimes called great conjunctions. Ancient astronomers found these events significant, and they inspired various predictions and interpretations. Worlds appearing to meet, seen from our vantage point alone. There are 5 points in space where the gravitational forces of two large bodies balance in such a way that a smaller object can remain stable. These are called Lagrange points, named after the mathematician Joseph Louis Lagrange, who calculated them. The Sun-Earth system has 5 Lagrange points. The James Webb Space Telescope orbits the L2 point, about 1 million miles from Earth on the side away from the Sun. At L2, the telescope can keep its sunshield between itself and the Sun, Earth, and Moon, staying cold enough to observe infrared light from the early universe. Points of balance, where gravity finds equilibrium. The Drake equation is a famous formula used to estimate the number of active, communicative, extraterrestrial civilizations in the Milky Way galaxy. It considers factors like the rate of star formation, the fraction of stars with planets, the number of planets that could support life, and so on. The equation was proposed by Frank Drake in 1961. The problem is, most of the variables are unknown. Depending on the values you plug in, the number of civilizations could be 0 or millions. The equation is less about providing an answer and more about framing the questions we need to answer through observation. A formula not for knowing, but for focusing our curiosity. The search for life beyond Earth is one of the driving forces behind solar system exploration. We've sent missions to Mars to search for signs of past or present microbial life. We're planning missions to Europa and Enceladus to sample their subsurface oceans. We're studying Titan's complex organic chemistry. Even if we find only microbes, it would be one of the most profound discoveries in human history. It would tell us that life isn't unique to Earth, that the universe is likely teeming with biology. And if life arose independently twice in one solar system, then it must be common throughout the cosmos. The question haunting every mission, are we alone? Many spacecraft have explored the solar system. Mariner missions visited Mercury, Venus, and Mars in the 1960s and 70s. The Pioneer and Voyager missions flew past the outer planets, sending back the first close-up images. The Galileo spacecraft orbited Jupiter for 8 years. The Cassini spacecraft spent 13 years at Saturn. New Horizons flew past Pluto and continues into the Kuiper Belt. The Juno spacecraft orbits Jupiter. The Parker Solar Probe is diving closer to the Sun than any previous mission. These robotic explorers are our eyes in space, revealing worlds we can't yet visit in person. Machines carrying our curiosity, sailing to worlds beyond reach. Some spacecraft carry messages intended for any extraterrestrial intelligence that might find them. The Pioneer plaques, attached to Pioneer 10 and 11, show a diagram of a man and woman, pneumon, the location of Earth, and symbols representing hydrogen. The Voyager Golden Records attached to Voyager 1 and 2 contain sounds and images representing the diversity of life and culture on Earth. These messages are unlikely to ever be found. Space is vast and the spacecraft are tiny, drifting slowly through the void. But the messages are more for us than for aliens. They're a statement that we exist, that we reached out. Bottles cast into the cosmic ocean, carrying our greeting. The solar system will continue to evolve. In a few billion years, the sun will expand into a red giant, engulfing the inner planets. The outer planets will become warmer, and their moons might temporarily have liquid water on their surfaces. Europa and Enceladus might briefly become habitable, though life developing in such a short window is unlikely. Eventually, the sun will shed its outer layers, creating a planetary nebula, and the core will collapse into a white dwarf. The white dwarf will slowly cool over trillions of years, eventually becoming a black dwarf. The planets, or what's left of them, will continue orbiting this stellar remnant in the darkness. All things have endings, even stars and solar systems. But that's so far in the future it's almost meaningless to us. For now, the solar system is stable, beautiful, endlessly fascinating. It's our home in the most literal sense. Everything that has ever happened in human history has happened here, within this system. Every person who has ever lived has lived under this sun. Every story, every discovery, every thought has occurred on one small world orbiting an ordinary star. And yet, we've reached out. We've sent our machines to touch other worlds. We've walked on the moon. We've gazed back at Earth from space and seen it as a fragile, precious place. Our home, vast to us, tiny in the cosmos. There are things we still don't understand about the solar system. We don't know exactly how the moon formed, though the giant impact hypothesis is the best model we have. We don't know what drives Uranus's and Neptune's internal heat. We don't know if there's a ninth planet, a large world far beyond Neptune's orbit, that might explain the clustering of certain Kuiper Belt objects' orbits. This hypothetical Planet 9 hasn't been observed, but some astronomers believe the evidence is compelling. Searches are ongoing. Mysteries remain, waiting for new eyes and new instruments. The more we learn about the solar system, the more we realize how dynamic and interconnected it is. The planets influence each other through gravity. The sun influences the planets through solar wind and radiation. Asteroids and comets move between orbits, occasionally colliding with the planets and moons, delivering water and organic molecules. The solar system is a system in the truest sense, not a collection of isolated objects, but a web of interactions playing out across billions of miles and billions of years. A community of worlds bound by gravity and time. Let's think about scale for a moment. If the sun were the size of a large beach ball, about 2 feet in diameter, Earth would be the size of a small pea located 80 feet away. Jupiter would be the size of an apple 250 feet away. Neptune would be a grape half a mile away. And the nearest star, Proxima Centauri, would be about 10,000 miles away. Space is mostly empty. The distances are almost incomprehensible. Yet gravity reaches across those voids, holding everything together. Vastness, punctuated by specks of matter, tied by invisible force. Humans have always looked up at the sky and wondered. Ancient astronomers tracked the motions of planets, which they called wandering stars because they moved against the backdrop of fixed stars. The word planet comes from the Greek word for wanderer. These early observers knew only the visible planets: Mercury, Venus, Mars, Jupiter, and Saturn. They didn't know they were worlds. They didn't know Earth was a planet. They thought Earth was the center of everything, with the heavens revolving around us. It took centuries of observation and thought to realize we're not the center. that we're one world among many, understanding growing slowly, overturning our central place. The invention of the telescope in the early 1600s revolutionized astronomy. Galileo turned his telescope toward Jupiter and saw 4 moons orbiting it. This was direct evidence that not everything orbited Earth. He saw phases of Venus, proving Venus orbited the Sun. He saw mountains and craters on the Moon, showing it was a world, not a perfect sphere. These observations help support the Copernican model of a sun-centered solar system, though Galileo faced significant opposition for his views. New tools, revealing new truths, challenging old beliefs. Each improvement in technology brings new discoveries. Better telescopes found Uranus, Neptune, and countless moons and asteroids. Spectroscopy allowed astronomers to determine what planets and stars are made of by analyzing their light. Photography captured faint details invisible to the eye. Radio telescopes detected emissions from Jupiter and the Sun. And finally, spacecraft gave us close-up views, landing on other worlds, walking on the Moon, touching the surface of Mars with robotic hands. Each generation seeing farther, understanding more deeply. The space age began in 1957 when the Soviet Union launched Sputnik 1, the first artificial satellite. That tiny beeping sphere opened the door. Less than 12 years later, humans walked on the Moon. The pace of early space exploration was breathtaking. Then it slowed. We haven't returned to the Moon since 1972. But robotic exploration has continued and expanded. We've sent spacecraft to every planet. We've landed on asteroids and comets. We're planning missions to Europa, to Titan, perhaps eventually to the ice giants. Progress, sometimes rapid, sometimes patient, always forward. Humans will likely return to the Moon in the coming years. NASA's Artemis program aims to establish a sustainable presence on the lunar surface. From there, we might venture to Mars. Mars is the next logical step for human exploration because it's relatively close. It has resources like water ice, and it has a day length similar to Earth's. A mission to Mars would take about 6 to 9 months each way, with astronauts spending a year or more on the surface waiting for the right orbital alignment for the return journey. It would be a monumental undertaking. Mars, waiting as humanity's next destination. Some people dream of terraforming Mars, transforming it into a world with a thicker atmosphere and liquid water on the surface, making it habitable for humans without spacesuits. This would take centuries, maybe thousands of years, and would require technology we don't yet have. We'd need to release greenhouse gases to warm the planet, melt the polar ice caps, and thicken the atmosphere. Some scientists think it's possible. Others think it's foolish to even try. Mars is its own world, and maybe we should preserve it as it is rather than remaking it in Earth's image. Dreams of remaking worlds, raising questions of ethics and possibility. Regardless of whether we terraform other worlds, the solar system offers resources. Asteroids contain metals, including rare and precious metals. The asteroid 16 Psyche, for example, appears to be largely metallic, possibly the exposed core of a protoplanet that lost its outer layers in a collision. Some estimates suggest Psyche contains metal worth $10,000 quadrillion, though such estimates are mostly meaningless. If we flooded the market with that much metal, prices would collapse. But the resources are there, and one day humans might mine asteroids for materials to build structures in space. resources drifting in the dark, waiting for distant needs. The concept of space colonies has been around for decades. Physicist Gerard K. O'Neill proposed large rotating habitats, cylindrical structures miles long, that would spin to create artificial gravity. These O'Neill cylinders could house thousands or millions of people, with parks and cities inside. They could be placed at Lagrange points or in orbit around planets. We don't have the technology or resources to build such structures yet, but they are theoretically possible. They represent one vision of humanity's future as a spacefaring species. Imagined homes in space, rotating gently among the stars. Another vision involves generation ships, massive spacecraft that would take centuries to reach other star systems. The people who started the journey would die long before arrival. Their descendants, perhaps dozens of generations later, would reach the destination. These ships would need to be entirely self-sufficient, with closed ecosystems providing food, water, and air. It's a sobering thought, committing generations to life in a metal world sailing through the void. But if we want to reach the stars with current technology, generation ships might be the only way. Journeys measured in lifetimes, destinations reached by descendants, or perhaps we'll develop faster propulsion. Ideas include nuclear pulse propulsion, fusion drives, antimatter engines, or even light sails pushed by powerful lasers. Each has its challenges, but if we could reach even a significant fraction of the speed of light, trips to nearby stars would take only decades instead of centuries. Alpha Centauri, the nearest star system, is about 4.3 light-years away. At 10% the speed of light, a journey would take 43 years. Still a lifetime, but within the range of a single human's experience. Dreams of speed, shortening the cosmic distances. But we're getting ahead of ourselves. We're still learning about our own solar system. There are moons to explore, asteroids to visit, mysteries to solve. Why does Venus rotate backward? What's beneath the clouds of Jupiter? What's in the subsurface oceans of Europa and Enceladus? Is there life anywhere else in the system? These questions drive our exploration. They pull us outward, encouraging us to build better instruments, send more missions, look more closely. Questions, the engine of exploration. The solar system is ancient, about a third the age of the universe itself. It will endure for billions of years more, but it's not eternal. Nothing is. Stars have lifetimes, planets evolve, moons spiral inward or outward, atmospheres are gained and lost, ice ages come and go. The solar system is a dynamic, changing place operating on timescales so long, they're difficult to grasp, yet here we are, brief sparks of consciousness, able to comprehend these vast cycles. We're made of star stuff, as Carl Sagan said, the universe pondering itself, temporary beings contemplating eternity. Let's return to Earth for a moment, to the blue marble spinning in the dark. Earth is the only world we know of with life. That makes it precious beyond measure. All the diversity of life, from bacteria to blue whales, from redwoods to reef fish, exists only here as far as we know. Earth's biosphere is a miracle of chemistry and evolution, a thin layer of living things clinging to a rocky world. We're part of that biosphere, completely dependent on it. And we're the only species aware that we live on a planet, one among many. Home, a rare jewel, perhaps unique, Certainly precious. Earth's position in the habitable zone, sometimes called the Goldilocks zone, allows liquid water to exist on the surface. Too close to the sun, and water would evaporate. Too far, and it would freeze. Earth sits in the narrow band where conditions are just right. But being in the habitable zone isn't enough. Venus is technically in the habitable zone, but runaway greenhouse warming made it uninhabitable. Mars is on the outer edge, and it's cold and dry now, though it might have been warmer and wetter in the past. Earth has additional factors that support life: a strong magnetic field, a large moon that stabilizes its axial tilt, plate tectonics that recycle carbon and regulate climate. Many factors aligning to make one world suitable for life. The history of Earth is written in stone, in layers of rock that record billions of years. The oldest rocks on Earth are about 4 billion years old. Life appeared by at least 3.5 billion years ago, maybe earlier. For most of Earth's history, life was simple, single-celled. Then, about 600 million years ago, complex multicellular life exploded in diversity during the Cambrian period. Life colonized the land about 450 million years ago. Dinosaurs ruled for about 165 million years before an asteroid impact wiped them out 66 million years ago. Humans appeared only in the last few 100,000 years. We're newcomers, billions of years condensed, ending with us, briefly here. If Earth's history were compressed into a single 24-hour day, humans would appear in the last few seconds before midnight. All of recorded history would fit into the last fraction of a second. Our presence is brief, cosmically speaking. Yet in that brief time, we've developed technology, science, art, music, literature. We've split the atom and walked on the moon. We've photographed galaxies billions of light years away and detected gravitational waves from colliding black holes. We've become aware of the universe and our place in it. A species, young but reaching, grasping at understanding. The solar system gives us perspective. It reminds us that we're part of something larger. Our concerns, our conflicts, our politics seem small when viewed against the backdrop of planets and stars. That doesn't mean they're unimportant. They matter enormously to us. But it's healthy to occasionally step back and remember the bigger picture. We live on a small world orbiting an average star in a vast galaxy containing hundreds of billions of stars in a universe containing hundreds of billions of galaxies. We're small, but we're also conscious, curious, capable of wonder. Smallness and significance coexisting. Carl Sagan called Earth a pale blue dot, a phrase from a famous photograph taken by Voyager 1 from beyond Neptune in 1990. In that image, Earth is less than a pixel, a tiny speck of light caught in a beam of scattered sunlight. Sagan wrote about that image, reflecting on how everyone who ever lived did so on that mote of dust, suspended in a sunbeam. All our wars, achievements, loves, and losses happen there, on that tiny stage. It's a humbling and beautiful perspective. Our world, a pixel in a photograph, holding everything we know. But the solar system is more than just a source of perspective. It's also a frontier, a place to explore, to learn, to potentially expand into. Some people look at the solar system and see resources and opportunity. Others see beauty and mystery. Both views are valid. The solar system can be many things to many people. It can inspire scientists and poets alike. Perhaps what's most remarkable is that we can know these things at all. We've talked about 100 facts, more or less, about our solar system. Some specific, like the temperature of Mercury or the size of the Great Red Spot. Others more conceptual, like orbital resonances or the nature of the heliopause. Each fact is a piece of a larger puzzle, a small window into understanding how our cosmic neighborhood works. But facts alone don't capture the feeling of the solar system, the sense of wonder it can evoke. Numbers and measurements pointing towards something larger. When you look up at the night sky, you're looking back in time. The light from the stars takes years, centuries, sometimes thousands of years to reach your eyes. When you look at Jupiter through a telescope, you're seeing it as it was about 40 minutes ago, the time it takes light to travel from Jupiter to Earth. When you look at Neptune, you're seeing it as it was 4 hours ago. The universe doesn't present itself to us in real time. We always see it as it was, never as it is at this moment. The sky, a museum of light, showing us the past, and yet everything is connected by gravity, by the solar wind, by the magnetic fields that reach across space. Information propagates at the speed of light. So if the sun suddenly vanished, we wouldn't know for 8 minutes. Earth would continue orbiting the point where the sun used to be for those 8 minutes, pulled by gravity that no longer has a source. Of course, the sun isn't going to vanish, but thought experiments like this reveal the strange nature of reality, where effects take time to propagate, where simultaneity is relative. Physics, revealing a universe stranger than intuition suggests. The solar system is full of extremes: the hottest surface, the coldest shadows, the fastest winds, the tallest mountains, the deepest canyons, the strongest magnetic fields, the most volcanic activity. Each world holds some superlative. Each has its own character, its own story written in geology and atmosphere. If you could visit each planet, each moon, you'd find landscapes more alien than any science fiction, yet all obeying the same laws of physics that govern Earth. Alien worlds following familiar rules. Some objects in the solar system are almost beyond description. Take Iapetus, one of Saturn's moons. Iapetus has a two-tone surface, one hemisphere bright white, the other dark as asphalt. The boundary between the two regions is sharp. Scientists think the dark material came from another moon's surface and accumulated on Iapetus's leading hemisphere as it orbits Saturn. Iapetus also has a ridge running almost exactly along its equator, giving it the appearance of a walnut. This ridge rises about 12 miles above the surrounding terrain. No one is entirely sure how it formed. A moon split between light and dark, wearing an equatorial ridge. Or consider Hyperion, another of Saturn's moons. Hyperion is irregularly shaped and tumbles chaotically as it orbits. Unlike most moons which settle into predictable rotations, Hyperion's rotation is chaotic in the mathematical sense, meaning it's impossible to predict its orientation far into the future. Hyperion's surface is covered in deep craters that give it a spongy appearance. Some of these craters are 6 miles deep. The moon looks like it's made of styrofoam, though it's actually ice and rock. A tumbling moon, unpredictable, porous. Then there's Miranda, Uranus's moon we mentioned earlier. Miranda's surface looks like it was assembled from pieces. There are heavily cratered regions next to smooth plains next to ridges and grooves. One feature called Verona Rupes is a cliff about 12 miles high, the tallest known cliff in the solar system. If you jumped off Verona Rupes, Miranda's low gravity means you'd fall for about 10 minutes before hitting the ground. Of course, you shouldn't jump off cliffs on moons, but the thought experiment is striking. A cliff so high, falling becomes a slow drift. Many moons in the outer solar system are strange because they're small and far from the sun, where different physics and chemistry apply. Water ice is as hard as rock. Methane and ammonia can be liquids. Volcanic eruptions spew ice instead of lava. These are called cryovolcanoes, and they've been observed on several moons. Enceladus's plumes are one example. Triton has nitrogen geysers. Even Pluto shows signs of ice. Volcanoes. The concept of volcanism exists on these worlds, but the substances involved are completely different. Volcanoes of ice, erupting frost. Think about what cryovolcanism really means for a moment. On Earth, we're used to volcanoes erupting molten rock at temperatures over 2,000 degrees Fahrenheit. The lava flows down mountainsides, glowing orange and red, eventually cooling into solid rock. But on these distant, frozen moons, the eruptions are just as dramatic, just as violent, yet they involve materials we'd consider frozen or liquid here on Earth. Imagine a geyser shooting water mixed with ammonia dozens of miles into space, freezing instantly into tiny ice crystals that catch the distant sunlight. That's what happens on Enceladus, constantly, endlessly. A different kind of eruption, cold instead of hot, yet just as powerful. The temperature difference between Earth's volcanoes and these cryovolcanoes is staggering. While our lava can reach temperatures of over 2,000 degrees, the materials erupting from these icy moons might be only a few degrees above their freezing point. On Enceladus, the water in those plumes is probably just barely liquid, perhaps only 32 degrees Fahrenheit, the freezing point of pure water. But with salts and other materials dissolved in it, the freezing point drops, allowing it to remain liquid in the moon's subsurface ocean. When it erupts into the vacuum of space through cracks in the ice shell, it immediately begins to freeze, creating a spectacular fountain of ice particles. Barely liquid, erupting into cold so profound it freezes instantly. Scientists have studied Enceladus's plumes extensively using data from the Cassini spacecraft. Cassini actually flew through the plumes multiple times, sampling their composition directly. The spacecraft's instruments detected water vapor, ice grains, salt, silica particles, and organic molecules, including methane and complex carbon compounds. The presence of silica is particularly interesting because it suggests hydrothermal activity on the ocean floor. Silica forms when hot water, heated by contact with rock, dissolves minerals and then cools. This is exactly what happens at hydrothermal vents on Earth's ocean floors. Chemistry in the plumes revealing secrets of the ocean below. Hydrothermal vents on Earth are oases of life in the deep ocean. They support entire ecosystems based not on sunlight, but on chemical energy. Microbes feed on chemicals like hydrogen sulfide emerging from the vents. Larger organisms feed on the microbes. These ecosystems exist in total darkness, under crushing pressure, yet they thrive. When scientists discovered hydrothermal vents in the 1970s, it revolutionized our understanding of where life could exist. If life can thrive at Earth's hydrothermal vents, Why not at similar vents on Enceladus's ocean floor or Europa's? Life in darkness, fed by chemistry, suggesting possibilities elsewhere. Triton's nitrogen geysers are different from Enceladus's water plumes, but they're equally fascinating. Triton is so cold that nitrogen, which is a P in Earth's atmosphere, freezes solid on Triton's surface. But beneath darker patches of surface material, the nitrogen ice can be warmed slightly by sunlight. This creates pressure beneath the surface. Eventually, that pressure builds until the nitrogen explodes upward in a geyser, carrying dark material with it. These geysers shoot nitrogen gas and dark particles up to 5 miles high. The material then settles back, creating dark streaks across Triton's pinkish surface. Frozen nitrogen, heated just enough to explode upward. What's remarkable about Triton's geysers is that they're powered by sunlight, not internal heat. Triton receives very little sunlight at its distance from the sun, yet it's enough. The dark surface material acts like a greenhouse, absorbing what little light reaches it and warming the nitrogen ice beneath. It's a delicate process requiring just the right conditions. Too much reflective ice, and there's not enough warming. Too little ice, and there's nothing to pressurize. Triton has found the balance, and so its geysers erupt year after year for who knows how long. Sunlight at Neptune's distance, still powerful enough to drive eruptions. Pluto's possible ice volcanoes are more subtle, more uncertain. The New Horizons spacecraft, during its flyby in 2015, photographed 2 mountains near each other on Pluto's surface. These mountains, informally named Wright Mons and Picard Mons, have unusual shapes. They're large, dome-like, with depressions at their summits. Wright Mons is about 2.5 miles tall and about 90 miles across. Their shapes are suggestive of volcanic structures, but there are no lava flows visible. Instead, scientists think these might be ice volcanoes that erupted a slurry of water ice, nitrogen ice, ammonia, and methane. Mountains on Pluto, possibly built by erupting slush. If Wright Mons and Picard Mons are indeed cryovolcanoes, they would be relatively young features, geologically speaking. Perhaps they formed within the last few 100 million years, maybe even more recently. This would mean Pluto was geologically active relatively recently, which raises questions. Pluto is small and far from the sun. Where does the internal heat come from? Tidal heating doesn't work because Pluto doesn't experience strong gravitational tugs from other bodies. Perhaps radioactive decay in Pluto's core provides enough heat. Or perhaps there's some process we don't yet understand. A dwarf planet, apparently active, challenging our assumptions. The study of cryovolcanism teaches us that volcanism is a universal process, not limited to Earth or to hot environments. Anywhere you have material that can melt or sublimate, anywhere you have pressure differences and pathways for material to escape, you can have volcanism. It's a fundamental way that planetary bodies release internal energy and redistribute material from their interiors to their surfaces. On Earth, it's molten rock. On Io, it's also molten rock but driven by tidal heating. On icy moons, it's water, ammonia, methane, nitrogen. The principle is the same even as the substances change, a universal process expressed in different materials. Some of these cryovolcanoes might be active for billions of years. Enceladus's plumes, for instance, seem to be ongoing. The surface around the south polar region, where the plumes emerge, appears young and fresh with few impact craters. This suggests the surface is constantly being renewed by material from the plumes falling back down. Over billions of years, Enceladus is slowly covering itself with fresh ice, erasing the scars of impacts, maintaining a youthful appearance despite being as old as the solar system itself. A moon perpetually renewing itself, staying young. Other cryovolcanoes might be episodic, erupting only occasionally when conditions are right. Triton's geysers probably depend on seasonal changes in sunlight. As Triton orbits Neptune and as Neptune orbits the Sun, different regions of Triton receive varying amounts of sunlight over decades and centuries. When a region is oriented toward the Sun, geysers can form. When it faces away, they shut down, only to resume when sunlight returns. It's a slow cycle playing out over Triton's long seasons. Eruptions tied to seasons, switching on and off over decades. The materials erupted by cryovolcanoes can tell us about the composition of the subsurface. They're samples from depths we can't otherwise reach. When Cassini analyzed Enceladus's plume material, it was essentially sampling the moon's ocean without having to drill through miles of ice. This is incredibly valuable for astrobiology. If there are organic molecules in the ocean, they'll appear in the plumes. If there are signs of biological activity, chemical signatures that might indicate life, they might also appear. Future missions to Enceladus could carry more sophisticated instruments to analyze the plumes in greater detail. Samples delivered conveniently into space for study. Europa doesn't have plumes as dramatic as Enceladus's, but there's evidence it might have occasional plumes of its own. The Hubble Space Telescope detected what appeared to be water vapor plumes erupting from Europa's surface in 2012 and 2016. These observations are tentative and need confirmation, but if Europa does have plumes, even intermittent ones, that would make studying its subsurface ocean much easier. A future mission could fly through a plume and sample it, just as Cassini did at Enceladus. Potential plumes on Europa, offering hope for easier exploration. The discovery of cryovolcanoes has blurred the line between volcanically active and geologically dead worlds. We used to think that small bodies cooled quickly and became inert, but now we know that moons like Enceladus, smaller than some asteroids, can remain active for billions of years if they have the right conditions. Tidal heating can keep a small moon warm inside. Radioactive decay contributes heat over long timescales. Even small amounts of ammonia or salts in water can lower the freezing point, allowing liquid to exist at lower temperatures. Small bodies, defying expectations, remaining active. This has implications for astrobiology throughout the solar system and beyond. If small icy moons can have subsurface oceans and active geology, then there are many more potential habitats for life than we previously thought. Europa and Enceladus are prime candidates, but Ganymede, Callisto, Titan, Triton, Pluto, and others might also have subsurface oceans. That's at least half a dozen worlds in our solar system alone. And if icy moons are common around gas giant planets in other solar systems, and if those moons can have subsurface oceans, then the galaxy might be full of potential habitats for life. Many possible homes for life, hidden beneath ice throughout the cosmos. The idea that life might exist in subsurface oceans is both exciting and humbling. Exciting because it expands the possibilities dramatically. Humbling because it means life, if it exists, might be completely inaccessible to us for generations. We can't easily drill through miles of ice on another world. We can barely do it on Earth. So if there's life in Europa's ocean, swimming in the dark, it might be a long time before we can confirm its existence. Unless we get lucky and detect some chemical signature in a plume, or unless we develop technology far beyond what we have now. Life potentially present, but out of reach, waiting. Still, the search is worth pursuing. Understanding whether life exists elsewhere in the solar system is one of the most profound questions we can ask. If we find even microbial life on Europa or Enceladus, it would tell us that life arises readily when conditions are right. It would suggest the universe is teeming with life. And if we don't find life, that's also informative. It would tell us that life is rare, that Earth is special, that we should cherish and protect the biosphere we have. Either answer, life found or not found, would reshape our understanding. Cryovolcanoes also affect the surfaces and atmospheres of these moons in interesting ways. Enceladus's plumes contribute to Saturn's E-ring, a faint ring of ice particles that extends from Enceladus's orbit outward. The plumes shoot material into space, and some of that material escapes Enceladus's weak gravity, spreading out into a ring around Saturn. So Enceladus is constantly feeding Saturn's E-ring, replacing particles that spiral inward and rain down onto Saturn or are blown away by the solar wind. Without Enceladus's plumes, the E-ring would fade over time. A moon feeding a ring, a connection across space. Triton's geysers contribute to its thin atmosphere. The nitrogen gas and particles they eject don't all fall back to the surface. Some enter Triton's tenuous atmosphere, which has a pressure only about 1/70,000th that of Earth's atmosphere. This atmosphere is slowly escaping into space, lost to Triton forever. But the geysers replenish it, at least partially. So Triton has a dynamic atmosphere, constantly being lost to space and constantly being replenished by surface activity, an atmosphere in balance between loss and replenishment. The colors of these cryovolcanic features can be striking. Enceladus's south polar region, where the plumes originate, appears bright and fresh. The cracks through which the plumes erupt, called tiger stripes because of their appearance, show up as bluish-green features against the white ice. These colors come from the different sizes and structures of ice grains in these regions. Triton's dark streaks, created by its nitrogen geysers, contrast sharply with the pinkish ice of its surface. The pink color might come from methane ice that's been altered by ultraviolet light and cosmic rays, creating complex organic compounds. Colors revealing composition, structure, age. As we learn more about cryovolcanism, we refine our understanding of how heat moves through icy bodies. Heat can be conducted through solid ice, but that's slow. Heat can also be moved by convection, where warmer material rises and cooler material sinks. In bodies with subsurface oceans, heat can be transported by circulating water, similar to ocean currents on Earth. And heat can be released explosively through cryovolcanic eruptions. Each of these mechanisms plays a role in shaping these worlds. Heat flowing, shaping worlds from within. The future of cryovolcanism research is bright. Multiple missions are being planned to study these moons in detail. NASA's Europa Clipper mission, set to launch in 2024, will make dozens of close flybys of Europa, studying its ice shell, searching for plumes, and mapping its surface. ESA's JUICE mission, the Jupiter Icy Moons Explorer, launched in 2023 and will study Ganymede, Callisto, and Europa. These missions will revolutionize our understanding of these moons and their potential habitability. Spacecraft on their way, carrying our curiosity forward. And beyond that, there are dreams of landing on these moons, of drilling through the ice, of sending submarines into the subsurface oceans. These are technically challenging goals, perhaps not achievable for decades, but they're not impossible. Engineers are already thinking about how to design a probe that could melt through Europa's ice shell, lowering itself on a tether, communicating through the ice, eventually reaching the ocean and deploying a submersible. It sounds like science fiction, but it's based on real science and engineering principles. Dreams of submarines on other worlds, exploring hidden oceans. For now, we study cryovolcanoes from orbit, from flybys, from Earth-based telescopes. We analyze the data, build models, test hypotheses. We piece together the story of how these moons work, how their interiors are structured, how energy flows through them. Each observation adds another piece to the puzzle, and slowly, patiently, the picture becomes clearer. These are not dead, frozen worlds. They're active, dynamic, potentially even alive with microbial life. They're worlds worth exploring, worth understanding, worth dreaming about. Worlds revealed, bit by bit, in their full complexity. The diversity of worlds in the solar system suggests that planetary formation is a complex, chaotic process. No two planets are exactly alike. Even Venus and Earth, which started similarly, diverged dramatically. The small difference in mass, distance from the sun, and random events like impacts led to completely different outcomes. This gives us pause when thinking about planets around other stars. We've discovered thousands of exoplanets, worlds orbiting distant suns. Each is probably unique with its own characteristics and history. Each world its own story, shaped by chance and physics. The Kepler Space Telescope, launched in 2009, revolutionized our understanding of exoplanets. By staring at a single patch of sky and watching for the tiny dips in starlight, when planets pass in front of their stars, Kepler discovered thousands of exoplanet candidates. We now know that planets are common. Most stars have planets. Some have multiple planets. The galaxy is full of worlds, a staggering thought, but we've only studied our own solar system up close. Everything we know about planets in detail comes from studying these 8 worlds and their moons. Our solar system, a laboratory for understanding all others. Let's think about time again, deep time. The solar system has existed for 4.6 billion years. Earth has been around for almost all of that time. Life has existed on Earth for most of that time. But humans, modern humans, have existed for perhaps 300,000 years. We've had agriculture for only about 10,000 years. We've had industrial technology for about 200 years. We've had spaceflight for 67 years. In the context of the solar system's age, human history is an eye blink. We're incredibly new to the neighborhood. Newcomers just beginning to look around. Yet in that brief time, we've learned an astonishing amount. We know the masses and orbits of planets. We know their compositions, their atmospheres, their temperatures. We've walked on the moon and driven rovers on Mars. We've sent probes to every planet. We've landed on comets and asteroids. We've detected water on moons and dwarf planets. We've measured the solar wind and crossed the heliopause. The pace of discovery has been breathtaking. Imagine explaining to someone from just 200 years ago what we know now. It would seem like magic. Knowledge accumulating rapidly, revealing the cosmos. And we're not done. Upcoming missions will visit Europa, searching for life in its ocean. The Dragonfly mission will send a rotorcraft to Titan in the 2030s, flying from location to location, studying its lakes and organic chemistry. Veritas and Da Vinci. Missions will study Venus in unprecedented detail, including dropping a probe through its atmosphere. The Nancy Grace Roman Space Telescope will search for exoplanets and study the universe's evolution. Each mission adds to our understanding, answering old questions and raising new ones. The future, full of journeys planned and discoveries awaited. But perhaps the most important thing about studying the solar system is what it teaches us about Earth. By seeing how other planets evolved, we better understand our own. Venus shows us what runaway greenhouse warming looks like. Mars shows us what happens when a planet loses its magnetic field and atmosphere. The outer moons show us that liquid water can exist far from the sun if there are other heat sources. These lessons inform how we think about Earth's climate, its habitability, its fragility. Other worlds as mirrors, reflecting lessons for our own. Earth is currently experiencing climate change driven by human activity, primarily the burning of fossil fuels that releases carbon dioxide into the atmosphere. This carbon dioxide traps heat, causing global temperatures to rise. We know this is happening because we can measure it. We can also look at Venus and see what happens when greenhouse gases dominate an atmosphere. Venus is a cautionary tale, an example of how a planet's climate can spiral out of control. Earth won't become Venus, but we can learn from the processes that made Venus uninhabitable. A neighbor's fate, offering warnings. The solar system also reminds us that Earth isn't guaranteed to remain stable. Asteroid impacts have caused mass extinctions in the past. They'll happen again, though hopefully not in our lifetimes or for many generations. Climate can shift dramatically over geological time due to natural cycles. Ice ages have come and gone. The continents drift, pushed by plate tectonics. Earth is a dynamic, changing planet. It has been many different things over its history, and it will be many different things in its future. Our job is to ensure humans can adapt and survive whatever changes come. Change as constant, requiring adaptation and foresight. Some people feel small or insignificant when contemplating the vastness of space. It's easy to feel that way. We're tiny creatures on a tiny world in a vast cosmos. But I think there's another way to look at it. We're the universe becoming aware of itself. We're matter organized in such a way that it can think, create, explore, wonder. That's extraordinary. The atoms in your body were forged in stars that exploded billions of years ago. You're literally made of stardust. And now those atoms have arranged themselves into a pattern that can contemplate the stars that made them. Stardust, thinking about stars. The solar system is our origin story. It's where we came from, how we came to be. The sun ignited, gravity pulled matter together into planets. One planet developed life. That life evolved, and eventually humans emerged. We're the result of 4.6 billion years of cosmic and biological evolution. Every step of that process was necessary to bring us here, to this moment, listening to facts about the solar system as you drift towards sleep. It's a privilege to exist, to be aware, to be part of this unfolding story, a long chain of events leading here to now to you. And the story continues. Humans will keep exploring. We'll send more missions, make more discoveries. We might find life on Europa or Enceladus. We might walk on Mars. We might establish permanent settlements on the moon. Or we might not. The future is uncertain, but the drive to explore, to understand, to reach beyond our current limits, that seems to be part of human nature. We've always looked at the horizon and wondered what's beyond it. Now our horizon has expanded to include other worlds. Horizons, always calling, always expanding. Let's bring our journey to a close. We've traveled from the sun to the edge of the solar system and beyond. We've visited planets and moons, asteroids and comets. We've talked about magnetic fields and orbital resonances, impacts and volcanism, ice and fire. We've thought about time and scale, about humanity's place in the cosmos. The solar system is vast and ancient, but it's also knowable. With patience and curiosity, we can understand it. And in understanding it, we understand ourselves a little better. A journey through space, leading back to self-knowledge. The solar system will continue its silent dance long after we're gone. The planets will orbit, the sun will shine, the moons will circle their parents. The universe doesn't need us to witness it, but we're here, and we do witness it, and that witnessing has meaning. We create meaning through our attention, our curiosity, our attempts to understand. The solar system is meaningful because we've chosen to study it, to care about it, to tell stories about it. Meaning created by attention and care. So as you settle into sleep tonight, think about your place in this grand system. You're on Earth, which is orbiting the sun at 67,000 miles per hour. The sun is orbiting the center of the Milky Way at 500,000 miles per hour. The Milky Way is moving through space toward the Virgo cluster. You're in motion, part of a cosmic dance that includes everything from the smallest moon to the largest galaxy. You're connected to all of it through the laws of physics, through gravity and light. You, part of the dance, moving through space. Rest well. Let your mind drift among the planets. Imagine standing on the shores of Titan's methane lakes, or watching Jupiter's great red spot swirl beneath you from a high orbit. Imagine the view from Pluto, where the sun is just a bright star in a black sky. Imagine floating in the silence of space, where there's no sound, only light and darkness and the slow movement of worlds. These places exist, they're real, and humans have touched them, if only through our machines. Dream of other worlds, real and waiting. The solar system is a gift, a cosmic inheritance. We didn't create it, but we're part of it. We're expressions of the same processes that form the planets, the same matter and energy. We're not separate from the cosmos. We're woven into it, made of it, sustained by it. The sun's light feeds the plants that feed us. The moon's gravity pulls the tides. We breathe air that's been recycled through countless organisms over billions of years. Everything is connected. No separation between us and cosmos, only connection. If you found these explorations helpful, if they've given your mind a place to rest, consider subscribing. There are more journeys ahead, more topics to explore. Perhaps next time we'll wander through deep time, or explore the lives of stars, or trace the history of life on Earth. There are endless stories in the universe, each one waiting to be told in the quiet hours before sleep. More stories waiting, more journeys ahead. For now, let yourself rest. Let the solar system turn without your attention. The planets will be there tomorrow and the next day, and for billions of years to come. They're patient. They'll wait. You've done your wondering for today. Now it's time for sleep, for restoration, for dreams. May your dreams take you to distant worlds or to peaceful places closer to home. May you wake refreshed, ready for another day on this beautiful, improbable planet we call Earth. Sleep well, traveler. The cosmos turns slowly on.